The next presentation is entitled Impressed Current Cathodic Protection and Structural Strengthening Intervention Technique. It will be presented by Feng and Ji-Hua. Feng is professor of Shenzhen University, is director of RILEM, vice president of the China branch of ACI. He has been studying the basic research and engineering practice of green and functional building materials for 30 years. He has published 6 academic books and 175 papers cited in Web of Science. Ji-Hua is also professor at Shenzhen University. He started in 2008 and he carried out original research work on ICCP-SS with Feng, and he is the main inventor of this method. Based on the research of this method, he has obtained over 10 research projects and a significant funding of over 5 million euros. The results have been granted 20 Chinese and American patents, and he has published 3 books and more than 80 papers cited in Web of Science. So please, Xing, Feng and Ji-Hua, the floor is yours. You may start whenever you're ready.
Thank you, Chairman. Thank you for introduction. Good afternoon, ladies and gentlemen. I'm Feng from Shenzhen University. I'm making the presentation with Professor Ji-Hua on behalf of our research team. The presentation includes following contents. The background is well known that the corrosion of steel rebars due to chloride is the most important problem of the durability of reinforced concrete structures, especially in the coastal environment. There are many methods have been developed to improve the durability of reinforced concrete. Generally, the electrochemical methods, such as cathodic protection, can prevent steel corrosion, and structural strengthening, which is most familiar for civil engineers, can improve the mechanical behavior of degraded structures. However, structural strengthening cannot fundamentally prevent steel corrosion. Therefore, the degraded structures may need repeated intervention through the service life, as shown in this curve. On the other hand, cathodic protection also has a drawback. It is not able to recover the mechanical properties caused by the steel corrosion in the early stage. Therefore, it sounds like such a natural idea to combine CP and SS to achieve the synthesized intervention of both steel corrosion and mechanical behavior. The research started from 2008. We noticed that aluminum alloy is more active than mild steel, and it is a commonly used anode material for sacrificial anode cathodic protection. Therefore, we tried to use aluminum as both sacrificial anode and strengthening material. However, the result was not so exciting, since potential difference between aluminum and steel is insufficient to drive the CP system due to high resistance of concrete. Then, how about carbon fiber composites, such as CFRP? This material has been well investigated and applied in structural strengthening. Since CF is conductive, then the idea came out that CF composite may be used as anode material at the same time. However, the potential of CF is much higher than steel. It means galvanic corrosion occurs when the two are in direct contact, where steel is sacrificed. This is totally outside as the aluminum alloy case. Therefore, another electrochemical solution implies current cathodic protection called ICCP may be used. These pictures show the structure and the working mechanism of ICCP. The traditional anode materials of ICCP include different forms of titanium, mixed metal oxide, and so on. Generally, SACP has been well developed and there are many international standards available, but the high cost of anode material prevents this mechanic from widely applications, especially in China. Let's take a look of structural strengthening and implies current cathodic protection. The layouts are actually similar, that they both use an additional material normally arranged at the out surface of RC structures to achieve the designed functions. Therefore, the synthesized intervention method of reinforced concrete, ICCP-SS, was proposed, where carbon fiber material works as both anode and strengthening material. Although the idea is clear, it should be noted that the anode material always suffer degradation, and this anodic degradation is much more serious than the corrosion in normal conditions. Therefore, we firstly investigate the dual functional behavior of carbon fiber composites. The anodic polarization was conducted on CFRP first. Then the tensile properties were obtained. It shows stable fading voltage, however, tensile strength of CFRP decreased with increasing applied charge densities. And the electrolytes also affected degradation. The tensile failure mode shows degradation of epoxy resin and the debonding between carbon fibers and matrix due to anodic polarization. The degradation starting from the interface with electrolyte, extending along the thickness direction. It is very interesting, as you can see from the results. The tensile strength of CFRP after polarization increase with the chloride concentration, no matter which current densities is used. When 3% chloride was used, the residual tensile strength is around 90%. Therefore, it indicates that chloride has positive effect of tensile behavior of CFRP after anodic polarization. To further study the mechanism, here we investigate the effect of chloride on the anodic behavior of single carbon fiber. From the EIS, we can observe the carbon fiber has a smaller surface electron transfer resistance in the solution containing chloride ions, which shows the ion diffusion control process, indicating that chloride ions can generally improve the surface electrochemical activity of carbon fiber. The current time curves show that the carbon fiber has a higher current response in the chloride solution, and its apparent current density and the charge load are greatly improved, thus extending its service life as an anode material. As can be seen from ICM, chloride ions can inhibit the oxidation cracking of carbon fiber under polarization, maintain the good microstructure of carbon fiber, and thus improve the tensile strength of CFRP after polarization. From the material aspect, this is why carbon fiber material can be used as both anode and strengthening material, and especially suitable for the coastal environment dominated by chlorine ion erosion. Now, I will introduce the development of ICCP-SS. There are some fundamental problems to be discussed. Consider a simple reinforced concrete cross-section. This leads to smaller current density and reduce anodic degradation. Therefore, the most efficient and direct way to increase the service life of ICCP-SS system is to design the larger anode area. This is also the reason why traditional ICCP anode is normally arranged at the outer surface of reinforced concrete. Based on this equation and still untested results, it can be calculated that with 2 millimeter thick CFRP, the anode service life is more than 40 years. This calculation is totally following the basic principles and can be used for other cross-sections. It indicates the anode service life always increases with CFRP thickness. Another key problem is the bond matrix. Typically, there are two kinds of bond matrix. Organic matrix, such as epoxy resin, and inorganic matrix, such as cementitious material. The bond matrix in ICCP-SS is not only to transfer strength, but also provide phase boundary of electrochemical reaction. It must be conductive and durable. Epoxy resin is not conductive. Some proven research try to use resin-containing conductive powders to achieve ICCP-SS dual functions. However, the mechanism of epoxy resin and the cementitious matrix in this case are totally different. The electrode reaction is a process of charge transfer between the electrode carrier and the ion carrier at the phase interface. Epoxy resin doesn't provide ion. Therefore, even with conductive resin, the reaction will still occurs at the interface between concrete and the resin. In this case, the CF works as a conductor, not anode. Considering durability of epoxy resin is not good, anode degradation makes the service life even shorter. On the other hand, cementitious matrix provides ions. Therefore, in this case, CF is a real primary anode, and the cementitious matrix is secondary anode. This makes the anode area even larger, and the system is even more durable. Selection of CFRC is also a key problem. After a series of research, we finally recommend continuous CF match and inorganic cementitious materials to form the composite anode by comprehensively considering the anode area, electrical conductivity, and material cost. Based on the above considerations, the ICCP-SS system was developed. As you can see, the steel corrosion was successfully prevented. It should be noted that during the long-term service of the CP, anode degradation and interface acidification are unavoidable. Chopped carbon fibers and other conductive materials were incorporated into the cementitious matrix to form conductive metal, forming a three-dimensional conductive network with a primary anode carbon fiber mesh. The effective anode area was thus increased, and the concentration of hydroxide ions in the interface region was reduced accordingly. Bond behavior was investigated with single shear, double shear, and pull-off tests. The specimens with designed CFRCM showed stable performance. And on that basis, a lot of works have been done on ICCP-SS member behavior, especially in static and fatigue loading conditions. It indicates by adopting a reduction factor of CF. The current design methods of CFRCM strengthening concrete structures are generally conservative. Case study. Now I'll briefly introduce a case study. In the repair project of bridge pairs of Guangzhou-Shenzhen Highway, which is the first and busiest highway in China. Here shows the on-site inspection and the corresponding construction design. After on-site preparation, such as materials and equipment, the construction was processed, including surface treatment, connecting bolts and wires and connection, followed by the application of CF matches, cement leveling, and wear protection. This picture shows the bridge pair after construction. With cooperation of industry, 2 Chinese construction standards of the technology have been published. Future work. As the most developed area of China, the demand of construction sand of Guangdong is incredible. Based on the technique which was originally developed for existing structures, we further apply ICCP-SS to new constructions. We are using ordinary steel reinforcement. Therefore, the technologies of reinforced concrete and composite structures, including design, fabrication, construction, can be keeping used. This is very important to promote a new material. Apart from the ordinary concrete research, interesting work is conducted on prefabricated structures. At present, the design of ICCP-SS seawater sea-sand composite slab and composite beam has been completed. Our research history at ICCP-SS can be traced back to 2008. We got our first national grant in 2009 and have been working on it ever since. A series of works have been made in the past 14 years, and our journey on this topic never ends. Finally, I would like to extend my sincere thanks to Professor Han Yingxu, Professor Tan Luping, and Professor Yoder Tamong for their help and support in this work. Thank you.
Thank you very much for your very interesting work and a very good presentation. Thank you. It was a pleasure having you here.